There's a very famous quote in Bhagavad Gita. What is yours today belonged to someone else yesterday and will belong to someone else the day after tomorrow. You are enjoying the fact that this is yours. And I think it completely applies to AWS Spot instances. If you're wondering how, you will definitely get the answer in this presentation. Good afternoon, everyone. My name is Chunky Gupta, and he's my colleague, David. We are software engineers at Yelp, and today we will talk about how Yelp saved millions of dollars using Spot Fleet. First, we will talk about Seagull, which is our in-house distributed system. Then we will talk about FleetMiser, which is our in-house auto-scaling engine. And we will finish off with the future of Seagull and FleetMiser. Before going into that, I would love to share with you all what Yelp is. Yelp is a company which provides a platform for people to read or write reviews and help them connect with great local businesses. As of Q3 2016, we have over 100 million reviews, and this number is continuously increasing. Oops. It looks like we have to stay at Yelp, talk more about Yelp. All right. OK. I will just use it. All right. So these are some of the terminologies which we will be using a lot during our presentation. We will represent a cluster of on-demand, reserved, and spot instances with the blocks of blue, gray, and green colors. This small cent symbol will represent a single spot instance. One spot market is basically a combination of an AZ, availability zone, instance type, and instance size. So what we have here is three spot markets. In some of our graphs, we will use resource unit a lot. And for simplicity, you can assume one resource unit is one CPU. A bundle or executor is simply a packet which contains set of tasks. Those tasks can be a test case, test method, or an image URL, depending on what kind of job we are running. Oops. So what is Seagull? Seagull is our in-house distributed system, which we have built in last 2 or 3 years. And we use Seagull to run jobs with huge concurrency. We run over 25 million tests in a day, and they spin up more than 2.5 million Docker containers in a day. Classifying photos based on different classifier models is also done on Seagull, and we classify around tens of millions of photos in less than a day. So classifying photos and running tests are much faster and cheaper in Seagull. So we are continuously working on adding more applications in Seagull. This is a high architectural diagram of Seagull, where developer triggers jobs, or we can say run. We internally call Seagull runs. So Seagull first creates multiple bundles. Number of bundles depends upon how many tasks are there in the bundle, in that job. So those bundles are then passed to scheduler, and scheduler is just running on top of Mesos. Scheduler checks with Mesos, are there enough resources available to run these bundles on the cluster? Let's assume, in this case, there are enough resources available to run all these bundles in the cluster. So all the bundles will now be scheduled across the cluster. So one thing to notice here is bundles from different jobs can be run on the same slave at any point of time. So If you are wondering, like, if you are interested in knowing more about Seagull, because Seagull is a system with various other components, so I will highly recommend you guys to go over to our last year's reInvent talk on Seagull. Now let's talk about the history of Seagull cluster. When we started with Seagull, we were on 100% on-demand instances. And if I remember correctly, until May or June 2015, we were on demand. And around July, we decided to use Spot instances. So we created another auto-scaling group with Spot instances in it, and we started using 75% Spot instances and 25% reserved instances in our cluster. Doing this change was relatively easy. We just had to make some API call changes. So once we moved from on-demand to Spot, we faced some challenges, because as you might know, if you are dealing with Spot, there is a risk of stability and availability that we will talk about later. So in December, after working on those challenges, we started using Amazon EC2 Spot fleet with the same percentage of 75% Spot and 25% reserved. Along with that, we also started using our auto-scaling engine, which we call FleetMiser. David will talk more about FleetMiser later. So in February 2016, what we did, we moved to 100% Spot with that auto-scaling engine enabled. So if you look at this slide, from May 2015, 100% on demand, to February 2016, we are 100% Spot. And we are not risking the stability and availability of the cluster. This was one very interesting fact. We will talk about how we solve the issues of stability and availability by using Spot. Let's look into the numbers. Initially, when we moved from on-demand to reserve plus Spot, we saved around 55% in cost. And later, or early in 2016, when we moved to 100% Spot, with auto-scaling engine, we saved another 60% in cost. So overall, we saved around 85% in our Seagull cluster cost. So you must be thinking, or you must be wondering why we decided to start using Spot suddenly. So as I mentioned, around May or June 2015, when we started horizontally scaling our cluster, one thing we observed, we saw our AWS bill for Seagull cluster was increasing. That was pretty obvious. But we said, is there a way we can save some money and scale our cluster continuously? So we knew it will not be an easy work to do, because we know on-demand comes with stability, and you will never risk losing that on-demand instance. So we decided, OK, let's explore other options. Let's explore options other than on-demand. So our first option, which we considered, was using reserved instances. Reserved instances are like you reserve an instance for a particular period of time, but you pay the cost upfront. As our Seagull cluster usage was pretty volatile, and we could easily leverage our in-house auto-scaling engine, FleetMiser, so we decided, let's not pay the cost upfront and only pay what we use for. So the other option which we had was Spot instances. With Spot, you can think Spot as like a two-faced man. If you're just following some simple rules, this man will be nice to you, and you and your cluster will live happily. But a naive strategy in this case might make this man turn his face and bite you. By that I mean, you might end up paying more than on demand for a period of time. We will look into it later. How is it possible? I will share with you what simple rules we are following and saving 80 to 90% in cost. Before diving into that, let's first see how spot price actually works. Suppose in this, there is one spot market where there are 7 instances available, and there are 3 users, user A, user B, and user C, and they are bidding $10, $5, and $1 respectively. And their need is 3 instances, 2 instances, and 4 instances. So what AWS will start doing is, AWS will first start fulfilling the requirement for a user who is bidding higher. So in this case, user A and user B will get all the instances they needed, but user C will only get 1, 2 instances. So most of the time, AWS is good enough to provide all the instances you need. But there are times when AWS do want to take back instances. One thing to notice in that, so one thing to notice here is the spot price is $1. So spot price is decided by the last fulfilled bid. So in this case, the last fulfilled bid was for user C, which is $1. So now let's assume AWS wants to take back 3 instances. So to do that, AWS will first start terminating instances from users who are bidding less. So what we just saw, user 3 lost both the instances, and user B lost that 1 instance. And one very important thing, if you have noticed, the spot price is now $5, which is the last fulfilled bid of user B. So user A and B both are now paying $5 for each instance rather than $1, which they were paying earlier. So as I was talking about the spot price increase, this is a publicly available spot price history of C3 at X large. So most of the time, the spot price is 80 to 90% cheaper than on demand. But sometimes it goes way above than on demand. So in this case, it went up to $16 for some period of time. So in scenarios when you lose an instance, or when you get outbid, you have to plan for termination. You have to have a highly fault-tolerant system. By that I mean, your application and your cluster should be resilient towards any instance loss. As I mentioned before, Seagull is a very highly fault-tolerant system. This graph, or this image, shows one Seagull run where there are around 300 different bundles, and each bar represents one bundle. So the green bar represents a successfully finished bundle, and the yellow one represents a failed bundle. And it failed because we got outbid where that bundle was running, and we lost that instance. So what, in this case, Seagull will do, Seagull will reschedule that bundle again on any different host. What if it happens again? We lose the instance again, Seagull will reschedule it again. So in this way, Seagull, or this application, is handling any instance loss we have. So in the previous example of user A, B, and C, we saw user B and C were not having the required capacity in the cluster. User B was having 1, and user C was having none. This shows that there is a need for a system to handle this failure. There is a need for a system to fulfill the requirement, even in case you lose some instances in any spot market. So for us, that system was AWS EC2 Spot Fleet. It makes sure your cluster is highly available. Let's see how it works. Suppose here there is one user who needs 9 instances in his cluster, and he is in 3 markets, US West 2A, 2B, and 2C. Let's assume this is for C3 at X large. The spot price for in these spot markets are there in the lower left corner. So initially, he got all the instances from those 3 different markets. So in this case, when US West 2A spot price goes up, AWS will take back those 3 instances, but Spot Fleet will bring up 3 new instances from other markets. So for this user, there will be a time for a few minutes when the capacity was only 6, but his eventual capacity of the cluster will remain intact. So for him, his cluster is highly available if he is not worried about those few minutes when he lost those 3 instances. So you must be thinking, my application is highly fault tolerant, my cluster is available, I'm in 3 markets, I don't risk the ability to lose the instances. So let's look into one example, or let's look into a use case or a case when this change in bid price happens very frequently. Let's assume now US West 2B price goes up and 2A price comes down. So again, the cluster capacity is 9, but the user is not having any instance in 2B. If it happens again, in this case, user does not have to worry about it because he is having 9 instances, what he needed. But one thing to notice here is he is only in 1 AZ, which is a little risky if you are talking about our scale. Another thing what can happen now is, suppose US West 2B price again goes up, and 2C price again goes up, and 2B price comes down. Along with that, user 2B does not have enough capacity to fulfill the 9 instances. So in that case, the user is now having 6 instances, but he needs 9 instances. So the question is, even if I'm using Spot Fleet, there might be a chance, most of the time, AWS or the bid price does not fluctuate or does not increase very frequently, but sometimes it can happen that you have less capacity as you need it to be in the cluster. So this actually happened back in July this year when spot price for C3 at X large was changing very frequently. So in these cases, there are 2 challenges which you have to think about. First is availability. As we saw in the previous slide, the user was only having 6 instances, but he needed 9. So you have to think about how you will handle this availability issue in your cluster. And the second problem is, or the second challenge which you have to think about is reliability. One thing which you could do here is you can easily set your spot price to $12.5 or more. And you will not face an issue. You will not have any interruption because of this fluctuation. But I don't think you would want to do that for an instance whose on-demand price is $1.6 and spot price mostly is 50 cents. I don't think you would ever want to bid $12.5 for that instance. So you have to think about how would you handle too much interruption. Because bidding higher is not a way to handle interruption. So when we had this issue, we applied a naive strategy. We moved back to on-demand for a few days and thought, let's be in on-demand and wait for the fluctuation to stop. And honestly, it didn't turn out to be a very good option for us because we burned our months of saving just by moving back to on-demand for a few days. I agree, on-demand instances comes with stability and availability. You will not lose them. Your applications will not have any issues. But on the other hand, as we were used to using spot and paying cheap cluster cost, we didn't want to use on-demand again. We had to come up with another solution and start using spot instances again. So we sat down as a team and said, how would we handle this issue? Is there a way we can again start using spot and go back to the same cluster cost which we were paying before? So we came up with another simple solution, but this time a stronger one. We came up with diversification. What it means is this graph shows the colored time series are resource units or the capacity of individual spot market, and the dotted one is the total cluster capacity. So we used to have only 3 spot markets in our cluster. What we have here are 30 different spot markets in our cluster. And even if we get outbid in 3, 4, or any small number of spot markets, our cluster total capacity is remaining intact. As you can see, in 3 spot markets we got outbid, but the total cluster capacity didn't hurt. So now the question is diversification very simple to do? It was not an easy task for us. Seagull was not very compatible with some of the instance types in spot market. And we had to use spot because those spot instances on which Seagull was not compatible, they were also 80 to 90% cheaper than on-demand. So making Seagull compatible was worth spending time for us. So we made Seagull compatible with those instances, and then we didn't have issues of stability and availability. Now, you must be thinking, now my cluster is stable, I diversified my spot fleet, and my application is also fault tolerant. We should go back to home and sleep, no incidents, no cluster loss, no instance loss. That's true. But as we all know, everything comes up with a trade-off. So as this graph shows the performance of different bundles in terms of execution time on different instance types. So on some instance types, our bundles were taking longer as compared to other instance types. So we had to trade performance for diversification. Or I should say, we had to trade performance for scalability, availability, and cost-effective cluster. We decided that's fine, let's keep it there because this performance was not hurting us a lot. So if any one of you is planning to use Spot Fleet or is already using Spot Fleet, so we recommend you all to not have any complex bidding strategies. Just be simple, bid a number. And two more things. Don't bid higher than what you are willing to pay for that instance. And last but not the least, diversify your cluster. Because diversification is the key of using Spot Fleet. So now David will talk about FleetMiser, which is our in-house auto-scaling engine. David.
Thanks, Chunky. So yeah, as Chunky mentioned, Chunky spent a lot of time talking about Spot Fleet, and one of the reasons why we wanted to use Spot Fleet is to take advantage of the fact that we could add and remove instances dynamically. And so I'm going to spend some time talking about FleetMiser, which is our in-house engine to actually do that. Now, you might be wondering, why do we need any sort of an auto-scaling engine in the first place? And so this graph shows an example of what happens at Yelp in an average day. So this graph shows the number of Seagull runs that are triggered by our developers in the course of performing tests on our website. And you can see that most of the activity is between 9 a.m. and about 7 p.m. In other words, when people are actually at work. There are some that are outside of that time window. We do have some offices in Europe, and so some of those runs are triggered by people in Europe or people who are working late. But you can see that the load on our cluster is very volatile. We need a lot of capacity during business hours, and we don't need so much capacity the rest of the time. The load is also very predictable. We need this capacity during business hours, during the week, on the weekends, and at night we don't need so much capacity. And so this makes our application a prime candidate for auto-scaling, which allows us to save even more money on our compute costs. So I want to give you a quick overview of how FleetMiser actually works. This diagram shows all of the different components that we take advantage of. So FleetMiser has a number of auto-scaling signals that take information from Elasticsearch, from DynamoDB, and it calculates various metrics and statistics as to when we need to scale our cluster up and down. It uses the results of those auto-scaling signals to actually interface with the AWS Spot Fleet and tell it, hey, scale up, scale down, add some instances, remove some instances, et cetera. It also then reports back all of the information about the current state of our cluster to our metrics and monitoring component. So we store information into Elasticsearch in DynamoDB. This creates a nice feedback loop into our auto-scaling signals. We also monitor the operation of our cluster and also FleetMiser using signal effects and Sensu. So we can track how the cluster is scaling up and down, what signals are controlling the cluster scaling, and so on and so forth. Finally, we do store a little bit of state in Zookeeper. These are things like the current AMI that we're using for our cluster, the Spot Fleet request ID. I'm not really going to go into that detail, but there is some state that we store there. So on this graph, I want to show you that, hey, our auto-scaling engine actually works. This graph is showing the capacity of our cluster in resource units. And as you'll recall, Chunky said that a resource unit you can think of as approximately 1 CPU. And so you can see that our peak capacity is between 12 p.m. and 7 p.m. This is when, again, most of our work is being done. We have around 1,200 resource units at this time. And then after 7 p.m., we start scaling back down. There's a small bump around 4 o'clock in the morning. This is when a lot of our developers in Europe are doing some pushes and deploys. And so we scale up a little bit there, and then we scale back down in preparation for the start of the next day. So this graph hopefully convinces you that we're doing what we're supposed to be doing. And so I want to talk a little bit about how we actually control the behavior of our auto-scaling. To do that, I want to look more in detail at our auto-scaling signals. So FleetMiser has a really nice plugin-based architecture for scaling signals. So there's two parts, well, there's really three parts to this. There's the data that is stored in Elasticsearch and DynamoDB. There's a configuration file, you can see an example of this on this slide, that specifies how the signal should operate. And then each auto-scaling signal is just a very small amount of Python code that actually checks to see what our cluster should be doing. So here's an example of a cluster overutilized signal. This is what it might look like in our configuration file. I'm not showing the Python code here. The Python code really is just looking to see what our CPU utilization in the cluster actually is. Is it too high? If so, then maybe we're running close to the limits of our cluster and we need to scale up a little bit. And our configuration file controls what too high means and how much we should scale up. So we've got a parameter in there, query period, which says that we want to look back at the cluster utilization over the last 10 minutes. We want to check the average CPU utilization and see if it's above our scale-up threshold, which in this case is 65%. If it is, then we want to add 100 units to our cluster. The last parameter in here that I haven't talked about yet is our priority. The way that our signals interface with each other is through this priority. So each signal is required to have a priority value, and we evaluate each signal in increasing priority order. And we just use a first come, first serve rule. So the first signal that fires that says, hey, we need to do something to our cluster, we take that one and we do whatever it says. So in this case, we might have a cluster underutilized signal, which does the converse. It says that, if there's too little CPU utilization, then we want to start scaling down. If that one is at priority 3, then that one will only fire if the cluster overutilized signal does not fire. And again, each of our signals, there's like 10, maybe 15 lines of Python code. So using this architecture, we're able to very powerfully control the behavior of our cluster with a very small amount of code. So this graph shows 3 of the 4 different signals that we're using right now. Unfortunately, I couldn't find a period in time where you could see all 4 of the signals operating at once, but we'll go over all 4 of them anyways. So the first 3 bars on this graph are in this light orange color, which is our cluster underutilized signal. The orange line, the orange time series on this graph, is showing our cluster capacity as it responds to these various auto-scaling signals. And so in the first 3 cases, the signals are saying, hey, we are not using our cluster very much. Let's scale down. And you can see that the cluster capacity over this period of time is actually scaling down as these signals are firing. We do have a minimum capacity on our cluster, which is around 150 units. And so you can see that after that 3rd bar, we don't scale down any further because we've hit our minimum capacity. We want to make sure that we have some availability at all times, regardless of how much it's being used or not. Now the next bar, this light purple bar, is an indication that some of our developers have submitted batch jobs, or Seagull runs. Now the way that our Seagull run process works is there's a whole bunch of steps that we have to go through before the job can be scheduled onto our cluster. So we build a bunch of code, we compile some things, we compress some things down. All of this stuff has to happen before we can start doing any actual testing work on it. And during that time, we can check to see if our cluster has enough capacity to be able to handle runs that are going to be coming. So this light purple bar says, hey, some of our developers have triggered Seagull runs. Do we have enough capacity? They haven't been scheduled yet. Do we have enough capacity to handle them in the next 5 minutes or so? Now, the first time this purple bar shows up, you can see that the cluster capacity doesn't change. And so what this means is that the signal said, oh yeah, we're not really doing very much on the cluster right now. We've got plenty of capacity to handle our batch jobs. The second time that this purple bar shows up, that this signal fires, We've already had a number of things scheduled on our cluster. We're doing some work, and now it says, oh, we don't have enough capacity on our cluster to be able to handle the incoming work, so let's start scaling up now so that we don't impact the performance of these incoming jobs. The two green bars that are on the very right-hand side of this plot are our cluster overutilized signal. I already talked about this on our last slide. It says, hey, we've got a lot of stuff going on our cluster right now. Let's just scale up some more to make sure that we can handle all of the work that we're trying to do. And then finally, I don't show this signal here, but we do have a historical usage signal. We track the usage and the size of our cluster over the past month, and we can tell that, oh, every fourth Thursday, there's a emergency build that happens, for example, that we need to be able to scale up for. This isn't a regular, I mean, it is a regular thing, but it doesn't happen every week. And so we have a signal that is able to track the history and say, hey, it's the fourth Thursday of the month. We don't have any capacity, or we don't have any jobs scheduled right now, but based on our historical usage, we know we're going to need some, and so we'll scale up anyways. So this is how our cluster scaling signals work. What I want to do next is I want to talk about how we actually interface with our Spot Fleet cluster. So there's two parts to this. The first is how do we scale up, and the second is how do we scale down. Let's talk about scaling up first. Scaling up is quite straightforward. When you create your Spot Fleet, there's a parameter that's your allocation strategy, and you've got a couple of options for that. You can choose a minimum price allocation so that whenever you add a new unit to your Spot Fleet, it tries to find the unit that lowers your costs the most. Or you can choose the diversified strategy. And as Chunky talked about in his portion of the talk, diversification is really, really important. It's more important to us than making sure that we get the minimum price instance every single time. And so we use the diversified allocation strategy. Now the way this works is suppose that FleetMiser says a signal has fired and we want to add 48 units to our cluster. So all we do is we call the Spot Fleet and we say modify the fleet capacity and add 48 units. Because we've created our Spot Fleet request with the diversified allocation strategy, we don't have to do any additional work. It will attempt to create new instances in all of our different spot markets. So in this example, it might launch one instance with 16 units in each of US West 2A, US West 2B, and US West 2C. Very simple, very straightforward. Scaling down, on the other hand, is a little bit more complicated. And the reason for this is that we need to have very precise control over what instances get terminated. We don't want to, for example, terminate any instances that are currently doing work, because this is going to impact our developers' productivity, and then we're going to hear about it. So the way that we do this, let's suppose that a signal has fired and said, our cluster is not being used very much, so let's scale down. So we want to terminate 48 units. The first thing that we do is we collect all of the instances in our cluster that are currently idle. And let's suppose that there are 4 instances in this case. There are 2 instances in US West 2A. One has 32 units, one has 16 units. And then there's 1 idle instance in US West 2B and 1 idle instance in US West 2C with 16 units each. So now the question is, okay, we're going to kill some of these. Which ones do we kill? Again, we want to maintain cluster diversity. We want to maintain it while we scale up, and we want to maintain it while we scale down. And there's no converse to the allocation strategy of when you scale down. So we have to actually figure out which instances to kill ourselves in order to maintain our diversity. And so what do? We look at the markets that currently have the most number of units in them. And so in this case, suppose that US West 2A is the market that has the most number of units, and we pick the instances to kill from that market first. And so we might kill the 32-unit instance in US West 2A. Now, our three markets that we're considering, maybe they have an equal number of units. We still need to kill off 16 more units because that's what FleetMiser requested. And so at this point, we just pick one arbitrarily. And so maybe we kill off this instance in US West 2C. By doing this, we're able to maintain the diversity of our cluster as we scale up and as we scale down. This next graph is going to show a picture of this. This is the same graph that Chunky showed you earlier in the talk. This shows the number of units in our cluster. Each of the colored time series is a different spot market, and the dashed line is the total capacity of our cluster. And you can see that at around 7, 8 o'clock, we start scaling down, and the number of units that we remove from each of our different spot markets is roughly the same. So as we scale down, we maintain diversity across our fleet in preparation for the next morning when we scale back up. And you can see as the scale up that the diversification strategy is doing its job. Now, some of you might be aware that earlier this year, Amazon released an auto-scaling feature for their spot fleets. This is something that as a part of your spot fleet request, you can just go in and you can say, I want to auto-scale my fleet according to this policy. There's a link to the blog post about that on our slide, which you can find after the talk. But for right now, I just want to talk about some of the differences and similarities between Amazon's spot fleet scaling feature and our in-house FleetMiser scaling. So first, Amazon spot fleet scaling is driven by CloudWatch metrics. So anything that you want to put into CloudWatch, you can alert on and use that as a trigger to scale your spot fleet up and down. And as we went through earlier in the talk, FleetMiser uses these custom Python scaling plugins to determine the fleet capacity. For the Amazon spot fleet scaling, you can instruct your spot fleet to scale by a constant amount. So you can say that when this metric fires, you want to add 10 units, 20 units, whatever. You can scale by a percentage, so you want to add 10% of your current cluster capacity, or you want to remove 15% of your current cluster capacity, or you can scale by a step function. So you can say that if the value of your signal is between 0 and 10, you want to add 5 units. If it's between 10 and 20, you want to add 15 units. And if it's greater than 20, you want to add 50 units. FleetMiser has a slightly more flexible capability here. You can scale by any arbitrary amount that you want to put in your Python code. So in particular, you can scale based on some complicated function of your signal input. We actually take advantage of this when we use our batch job scaling. We have to convert the number of batch jobs into an expected number of units that we need, and then we compare that to our current cluster capacity to determine how much to scale up. The big reason why we are continuing to remain with FleetMiser for the time being is that the Amazon spot fleet scaling doesn't give you the capability to control how you scale down. You can scale down, but we can't say something like, don't kill off instances that are currently doing work. And this is really, really important to us. And as you saw in FleetMiser, you can actually specify what instances specifically you want to kill off. So if you're going to use spot fleet, or maybe you're using spot fleet right now, and you want to start auto-scaling, I definitely recommend that you start off with the Amazon spot fleet feature, or the Amazon spot fleet scaling feature. This is a really easy way to get your cluster auto-scaling. It uses a lot of technologies that I'm sure you're already using in CloudWatch. However, if you need any very sophisticated scaling logic, such as what we use in FleetMiser, then it might be time for you to start thinking about building something in-house. So this is everything that I want to talk about with respect to the current state of Seagull and with FleetMiser. I want to spend the last few minutes of our talk discussing what are some future goals and challenges that we hope to overcome with these products. So one goal that we would like to diversify our spot markets even further. As Chunky mentioned, we're doing a lot of photo classification work, and so maybe we want to start adding in some GPU instances to be able to handle those photo classification jobs. We also would really, really like to start using some of the larger instance types. For example, the X132X large has the capability of scheduling 53 simultaneous bundles at the same time. And we actually had the X132X large in our cluster for a while, and it was really cool. We were able to do a lot of work on it. The problem that we had is that each one of those 53 bundles was talking to a single instance of a Docker daemon. Each bundle spins up a bunch of Docker containers, and when you have 53 of them talking to one Docker daemon on one host, then everything kind of goes haywire, and it turned out that X132X large just ate Docker. And so we are not actually using X132X large right now, but we are trying to figure out how can we make our bundles talk with Docker in a better way so that we can get this instance back in our cluster, because it was really cool. Another goal that we would really like to add into FleetMiser is we'd like to be able to combine and control multiple different spot fleets and auto-scaling groups all as the part of the same cluster. So you might have an application where you want to have some minimum capacity that's always available. Maybe you want that on demand or reserved instance or whatever. And then you have 2 or 3 different spot fleet requests that you want to also control. We have a few situations where we'd like to be able to do functionality like this. And right now, FleetMiser doesn't have the capability to do this. So this is something that we would really like to add in. Another goal that we're going to be working on is how can we extend the scale down logic in FleetMiser? So if you'll recall, in the example that I showed you before, we kill off the 32-unit instance, which is just fine. This allows us to maintain diversity. But then I said we pick the next instances to kill off somewhat arbitrarily. And maybe we'd like to do something a little bit more intelligent. For example, looking at the cost of the various instances. So you can see here, maybe at this point in time, the instances in US West 2A and US West 2B are currently more expensive than the instance in US West 2C. In the old example, if we killed off the instance in US West 2C, then we'd be paying more than if we killed off one of the instances in US West 2A or 2B. And so maybe we can start taking advantage of some pricing information into our scale down logic so that we can actually kill off instances that are costing us more money. The last goal that I'm really excited about, this is a project that I've been working on and will be continuing to work on through the next year, is to actually figure out better ways to schedule our tasks onto Seagull. This will allow us to take better advantage of the resources that we have as a part of our AWS Spot Fleet cluster. And so what does this look like? I'm just going to give you a brief highlight about it, and then maybe I'll come back here next year and I can talk about all the cool stuff that I've done. But the idea is pretty simple. We have a bunch of tasks. They have various resource requirements. So maybe task A needs 100 megs of RAM. It needs 3 CPUs. And maybe it has dependencies on some various services. So it calls out to DynamoDB. Maybe it calls out to some other external APIs or some internal services at Yelp. We have another task that has many fewer resources. It only needs 10 megs of RAM. It only needs 1 CPU. And it has a different set of service requirements. What we'd like to be able to do is group tasks together in a way that combines the resource requirements and the service requirements. So in this example, maybe host 1 is a host that has a lot of CPUs available to it. It has a lot of memory available. And so we schedule our more resource-intensive tasks on that host, and we also try to schedule tasks that depend on similar services together. And then here we have host 2. Maybe it has a smaller number of resources, and so we schedule tasks that don't have as high of resource requirements. And again, we're trying to group by various services. And the hope is that this will allow us to schedule more stuff on our existing cluster so that we can do more work with the same amount of resources, and then leverage even further the Spot Fleet cluster that we have. So in conclusion, I'd just like to give you Yelp's simple mantra for saving money on your compute costs. First thing to do, you need to make sure you have a fault-tolerant application. As Chunky talked about, you need to have application-level fault tolerance because you don't know when instances might get taken away from you. And you also want to make sure that you have cluster-level fault tolerance. Cluster-level fault tolerance just means diversification. The second thing, if you know that your application or your use is very volatile, you might want to consider using some sort of an auto-scaling engine, whether this is the engine that's provided by Amazon or if you need something a little bit more complex and you need to come up with something in-house. But these two features will allow you to save a lot of money on your compute costs. If you'd like to find out any more information about the stuff that we're working on, whether it's Seagull or FleetMiser or anything else, you can follow us on Facebook and Twitter. We have an engineering blog where we regularly release information about products that we're working on. And we also maintain a lot of open source code, which you can find on GitHub. So that is everything we have to talk about. Thank you very much. And please remember to complete your evaluations.